Good morning, everyone. Previously, we explored the general characteristics of external flow, how Reynolds number determines whether the flow is dominated by inertia or viscosity, and how objects experience both pressure and shear forces that combine into lift and drag. So, today we would be exploring one of the most elegant and powerful concepts in all of the fluid mechanics, that is the boundary layer concept. So this idea, proposed by Ludwig Prandtl in 1904, fundamentally changed how we analyze the fluid flow. In fact, it's fair to say that without the boundary layer theory, modern aviation, weather prediction, and even sports equipment design would be impossible. Here is what we will be covering: the structure and the thickness of the boundary layers, the difference between the laminar and turbulent flow, how to calculate the boundary layer parameters, and perhaps most importantly, what happens when things go wrong and the boundary layer separates from the surface. So let us start with the very fundamental concept. When Reynolds number is large, and by large I mean sufficiently large that inertial effects dominate, the flow field can be divided into two distinct regions. First, there is the boundary layer, a thin region adjacent to the surface where the viscous effects are crucial. This region exists because of the no-slip condition, and the fluid must stick to any solid surface it flows past. Within this thin layer, velocity gradients are enormous, and so even with small viscosity, shear stresses are significant. Secondly, there is a region outside the boundary layer and in the wake behind the object where the velocity gradients are small and the fluid behaves essentially as if it were inviscid. The viscosity is exactly the same throughout the entire flow field, but its effects are only felt where the velocity gradients are large. So this is Prandtl's genius, recognizing that for large Reynolds number flows, we can treat the problem as two simpler problems: an inviscid flow outside and a viscous boundary layer near the surface, and match them together. So now let us consider the simplest case, a flat plate parallel to the flow, which is shown by this particular figure. And it also shows that what happens to the fluid particles as it enters the boundary layer. Outside the boundary layer over here, a small rectangular particle along flows along with distortion. It translates but does not rotate or deform. The flow there is irrotational, meaning zero vorticity. But watch what happens when the particle enters the boundary layer. Because of the flow gradient, flow velocity gradient, the faster fluid above, slower fluid below, the particle begins to distort. The top moves faster than the bottom, so the rectangle shears into a parallelogram. It also begins to rotate. Now, the flow within the boundary layer is rotational. It has non-zero vorticity. This vorticity is generated right at the wall because of the no-slip condition and diffuses outward into the boundary layer. At some distance downstream, if conditions are right, the boundary layer may become turbulent. Then the fluid particles become greatly distorted by random irregular motion. Mixing occurs not just at the molecular scale but with the finite sized eddies. Now, there are three ways to measure the thickness of the boundary layer. As shown in this particular figure, we have an important question over here: that where exactly does the boundary layer end? Where is the edge? So, in reality, there is no sharp edge. The velocity approaches the free stream value asymptotically as we move away from the wall. So, we need a definition over here. Standard boundary layer thickness, which is denoted as the sigma. This is arbitrarily defined as the distance from the plate where the velocity reaches 99% of the free stream velocity. But why 99%? Why not 98% or 99.95 percent? So this arbitrariness lead to more physically meaningful definitions. of the displacement thickness, which is hereby denoted as sigma star. Now look at this particular part B of the figure. Because of the velocity deficit within the boundary layer, the flow rate across the vertical section is less than it would be if the flow were uniform. So the displacement thickness represent how far we would have to displace the plate outward to get the same flow rate within the uniform velocity. So here is the mathematical representation of the displacement thickness sigma star. Now think of it this way, that the boundary layer pushes the external streamlines outward by this amount. Streamlines outside the boundary layer are displaced away from the wall because some fluid is missing near the surface due to the velocity deficit. There is another term which is the momentum thickness theta. This relates to the momentum flux. The momentum deficit in the boundary layer, the fact that the fluid inside has less momentum than it would at the full speed, can be expressed as a thickness of the fluid moving at the free stream velocity, and can be represented by this particular equation as represented on this slide, where sigma star and theta are crucial for the drag calculations, as we will be seeing in the subsequent topics. Now, for a flat plate, if the boundary layer is thin, we have the sigma and sigma star and theta all much less than the x, the distance from that is the distance from the leading edge. Now, this thinness is essential to the boundary layer theory. Now, let us get into the mathematics, but I promise to keep it conceptual. The full Navier-Stokes equations governing the fluid flow are incredibly complex, nonlinear partial differential equations that no one has solved analytically for any shaped body. But Prandtl realized that for large Reynolds number flows, we can simplify it. Because the boundary layer is thin, the velocity normal to the plate is much smaller than the velocity parallel to the plate, and changes across the boundary layer are much greater than changes along it. So this leads us to the boundary layer equations, which is hereby represented by the continuity and the momentum equations. So notice something remarkable over here, that the pressure has disappeared. For a flat plate, the pressure is constant throughout. The flows represents a balance between the viscous and the inertial effects only. Now these equations are still nonlinear partial differential equations, but there are simpler than the Navier-Stokes equation. And most importantly, they are parabolic. So information only travels downstream, not upstream. So what happens downstream cannot affect what happens upstream. In 1908, Prandtl student Blasius found a way to solve these equations. He introduced a similarity variables eta, which is hereby represented as eta equals to y under root u over nu x. So the key insight is that the velocity profiles at different x locations should be similar in shape when plotted against y over sigma, and from the force balance, sigma grows like under root nu x over u. So using this similarity variable, Blasius transformed the partial differential equations into an ordinary differential equation, which is represented in form of the f triple bar plus f uh, f double derivative equals to 0. So this is the Blasius equation. It's non-linear, but it's an ordinary differential equation that can be solved numerically. Now the solution gives us the velocity profile as shown in this particular figure and tabulated in this particular table also. From this we can get the crucial results for the boundary layer thickness, the displacement thickness, and the momentum thickness. So all of these equations, the final results are written over here. So notice that all three grows like under root x and are inversely proportional to under root u. So double the distance from the leading edge and thickness increases by about 40%. Double the velocity and the thickness would decrease by about 30%. So the wall shear stress here would be tau w equals to 0.332 u raised to the power 3 by 2 under root rho mu over x. So this decreases with the x, the boundary layer thickens, so the velocity gradient at the wall becomes smaller, and it varies as u raised to the power 3 by 2, not u, not simple the u. So a key difference from the fully developed pipe flow, which we have discussed in the previously discussed topics. So now discuss about the momentum integral boundary layer equation. We obtaining the Blasey solution required mathematical sophistication, as we have seen in the previous slide. But there is an alternative approach that's both simpler and more versatile. The momentum integral method developed by the von Karman in 1921. So now consider a control volume from the leading edge to some location x, extending from the plate up to a streamline just outside the boundary layer, applying the momentum equation on it. So what do we find over here? The drag on the plate that equals the deficit in the momentum flux at the outlet. Now, in terms of the momentum thickness, drag can be represented as d equals to rho b u square times theta. So this is beautiful. The drag is directly related to the momentum thickness, and as the x increases, sigma increases, theta also increases, and drag increases. So the thickening boundary layer is necessary to overcome the viscous shear stress on the plate. So differentiating with respect to the x, this particular equation would be transforming into the momentum integral equation. We would get the equivalent tau w equation as displayed. The wall shear stress equals rho u square times the rate of increase of momentum thickness. So here is the brilliant part, that even if we don't know the exact velocity profile, we can assume a reasonable shape and get surprisingly accurate results. So suppose we assume a linear profile, small u over capital U equals to small y over sigma, then we can get the momentum thickness wall shear stress equation from the Newton's viscosity law, and plugging it into the basic relationship as tau w equals to rho u square d theta by d of x, we can get the final relationship, and comparing it with the Blasius, which states 5 under root nu x over u. So this constant is very different, 13% low for the thickness, but the functional form is exactly right. This approximate method with minimal effort captures the essential physics. Now, this particular table also shows the results for various assumed profiles. The more accurate the assumed shape, the closer the constant gets to the Blasius value of 5. Now, here is the crucial question. How long can a boundary layer remain laminar? So the answer to it depends on the Reynolds number. For any free stream velocity and any fluid, if the plate is long enough, the boundary layer will eventually becomes turbulent. So the transition occurs at the critical Reynolds number, which we would be representing as Rex critical equals to Ux critical divided by nu. So for a flat plate with a sharp leading edge in a typical airflow, the transition occurs somewhere between Reynolds number value of 2 exponent 5 and 3 exponent 5. So we will be using the Reynolds number critical Reynolds number as 5 exponent 5 as a standard value over here. So what determines exactly where the transition occurs? So there are several factors. One of them is the surface roughness. Rough surfaces trigger the transition earlier. Second one is the free stream turbulence. More turbulences or disturbances in the flow promote earlier transition. And the third one is the pressure gradient. Favorable gradients delay the transition, and adverse gradients accelerate it. So transition is not a single point, it occurs over a region. Turbulent spots appear randomly, grow rapidly as they are convected downstream, and eventually merge to cover the entire surface. So this particular figure shows this beautiful process, and those turbulent spots looking like elongated wedges growing in the flow direction. So as this figure shows, the Turbulent profiles are dramatically different from the laminar ones. They are flatter, have a steeper velocity gradients at the wall, and produce the thicker boundary layers. So now moving on to the turbulent boundary layer flow, the turbulent boundary layers are complex, random, and irregular. The velocity at any point fluctuates unpredictably. The flow consists of intertwined eddies of different sizes, some tiny, some comparable to the boundary layer thickness itself. Here is what makes the turbulent flow fundamentally different from the laminar one, because the transport occurs through the motion of finite-sized fluid particles, not just the molecular diffusion. Fluid particles moving towards the plate carry excess momentum from regions of higher velocity. Particles moving away from the plate gain momentum from the fluid. So this random cross-stream transport extracts the momentum from the flow much more efficiently than the molecular diffusion alone. So the result is that the shear stress in a turbulent flow is considerably greater than in laminar flow at the same Reynolds number. Now, because there is no exact solution for the turbulent flow, we don't have a precise expression for turbulent shear stress. We rely on the empirical relationships, but the momentum integral equation still works. Now, here in this particular example problem, it assumes that 1 by 7th power law velocity profile. This approximates the experimental profiles well, except very near the wall where it gives infinite velocity gradient, a limitation but acceptable for integral methods. Now, combined with an empirical shear stress formula, which is represented over here as the tau w equals 2.0225 rho u square. So bracket nu by capital U sigma raised to the power 1 by 4. So this result into the more comparable with the laminar flow as sigma over x equals to 5 over Reynolds number raised to the power 1 by 2. So the turbulent boundary layer grows faster. X raised to the power 4 by 5 versus x raised to the power 1 by 2, and are much thicker at the same Reynolds number. The shear stress decreases as x raised to the power minus 1 by 5 rather than x raised to the power minus 1 by 2. So this particular figure also shows the friction drag coefficient for flat plates over the full range of Reynolds number and roughnesses. So like the Moody diagrams for pipes, this is an essential engineering tool. Now, so far, we have only considered the flat plates with constant pressure, but most real objects, airfoils, cylinders, cars, have curved surfaces where the pressure varies along the flow. So, for a curved body, the free stream velocity at the edge of the boundary layer, which hereby can be represented as U subscript Fs, varies with the location x. And from the Bernoulli equation, the velocity changes, pressure changes as dP over d of x relationship over here. So this pressure gradient is imposed on the boundary layer. Pressure is essentially constant across this thin boundary layer but varies along it. So consider inviscid flow past a circular cylinder. The velocity along the surface goes from zero at the front stagnation point to two times of the free stream velocity at the top, back to zero at the rear. The pressure correspondingly drops from stagnation pressure at the front to minimum at the top, then rises back to stagnation at the rear. So the decreasing pressure from front to top is a favorable pressure gradient. It helps the flow accelerate. The increasing pressure from top to rear is an adverse pressure gradient. It opposes the motion trying to decelerate the flow. Now, a fluid particle outside a boundary layer goes down and up this pressure hill with no energy loss. It exchanges kinetic and pressure energy perfectly. But a fluid particle inside the boundary layer experiences the viscous losses also. It does not have enough energy to climb all the way up the adverse pressure gradient. At some point, it stops. The velocity gradient at the wall becomes zero and the flow separates from the surface. So, this is the boundary layer separation. Beyond this point, we get a reverse flow near the wall. The boundary layer lifts off, creating a wake of recirculating fluid. So the separated region has much more lower pressure than the front, creating the pressure drag, even though the viscous shear stress itself might be small. So this explains the D'Alembert's paradox. Inviscid theory predicts the zero drag, but for real fluids, no matter how small the viscosity is, it produces the drag because of separation. Now, the turbulent flow has also its advantage. Here is where it gets really interesting. A turbulent boundary layer has more energy. The velocity profile is fuller, and there is additional energy in the fluctuating motion. So a turbulent boundary layer can travel farther into an adverse pressure gradient before separating. Now, this C part of this particular figure shows this dramatically. For a circular cylinder, the laminar boundary layer separates around 80 degree from the stagnation point. The turbulent boundary layer, however, stays attached around 120 degree, much farther around the back. So this narrower wake means lower pressure drag. That is why the golf balls have dimples on it. The dimples trip the boundary layer to turbulent at a lower Reynolds number, reducing the drag and allowing the ball to travel farther. The same principle applies to airplanes' wings. At high angle of attack, turbulent boundary layers delays the stall process, allowing the higher lift before separation. Now, momentum integral with the pressure gradient. To handle the boundary layers with pressure gradients, we need a more general form of the momentum integral equation over here, including the pressure forces in the control volume analysis, which would give us this particular equation. So this is the representation of the balance between the viscous forces, the pressure forces, and the fluid momentum through the boundary layer thickness. So for a flat plate, u f of s is constant, but du over d of x equals to 0, and this reduces to our earlier equation, which is the tau w equals to rho u square d theta over d of x. So this general equation allows us to analyze the boundary layers on arbitrary curved surfaces using the free stream velocity disturbances from inviscid flow theory. While the details are beyond our scope, the concept is crucial. Pressure gradient fundamentally alters the boundary layer behavior and determines whether the separation occurs. Now, let us summarize what we have learned in this particular lecture, that at very high Reynolds number, the flow divides into a thin boundary layer, viscous, rotational, and outer inviscid region. Secondly, the boundary layer thickness can be defined in multiple ways, sigma, sigma star, and theta. Thirdly, laminar boundary layer follow the Blasey solution. The momentum integral method gives approximate results with minimal effort. Then we discussed that the transition to turbulent flow occurs at the critical Reynolds number of value 5 exponent 5, producing fuller profiles and higher shear stress. Then the pressure gradients dramatically affect the boundary layers also. Adverse pressure gradients causes a separation. And lastly, we discussed that the turbulent boundary layers resist the separation better than the laminar ones. So next time we will be building on this foundation to explore the drag concept, how the friction drag and pressure drag combine, how drag coefficients depend on shape and Reynolds number, and why some objects have surprisingly low drag while others have surprisingly higher drag. So we will be seeing how the boundary layer separation determines the pressure drag and how streamlining works by delaying the separation. So we will be also exploring the real world applications from the golf balls to tractor trailers to submarines. So for today, Remember that the boundary layer is where the action happens. Outside it, the flow is simple and inviscid. Inside it, the viscosity rules, velocity gradients are huge, and the fate of the entire flow field, whether it separates or not, is determined. So, up for now, see you next time. Thank you.